So, I think you have seen the two videos, practical videos, right? That I have uploaded. And the first one was the one where we interacted and through the online
স্যার
class.
রেকর্ডিংটা অন করে স্যার
হ্যাঁ বলো।
স্যার রেকর্ডিংটা অন করে দিন।
আচ্ছা ঠিক আছে, দেখছি আমি। না, রেকর্ডিংটা অনই আছে। রেকর্ডিংটা অন আছে, আমি সেপারেটলি রেকর্ডিং করছি, ঠিক আছে?
ঠিক আছে স্যার।
Okay. Now you see, we have discussed about a lot of things. On the first class, I talked to you about the very, what should I say, basic aspects of gamma ray spectroscopy. I talked to you about what has to be done for this practical, where we are supposed to perform a basic study of a gamma spectrum from a decaying nucleus, which decays predominantly by gamma ray. Now, during the second class, I did the demonstration in the lab, and then in the lab we have the blackboard, and there I talked to you about the various other aspects of our practical, which was quite difficult to show on pen and paper or through the PowerPoint slide. Now, and I also gave you two files. The first one was basically the theoretical file, which has the basic ideas about the theory, which is required for proper understanding of this practical, and the second one is what you have to do. Now this file that I am going to present to you right now, it does have that second file as well. So since I have already discussed to you most of the theoretical stuff which was there in the first file, now I will try to talk to you about the second one, and basically we will talk mostly about what needs to be done in the lab for this practical, apart from taking the data which we have already discussed yesterday during the practical demonstration. So on the screen you can see here, so this is our detector, or should I say gamma spectrometer, and this is the radioactive source, the 137 cesium source you can also see, and this is our compact electronic module which has got both the linear amplifier and also the single channel analyzer along with scaler and timer. Not to forget that we also have a knob here through which we can give the high voltage to the detector. Now for the preamplifier, the high voltage, or it doesn't need any high voltage, normal voltage that is fixed, and as I have shown you yesterday, it comes out from the back of this module and enters here, the second one. Okay, now, and this is the real setup in the world, and the pictorial or the block diagram here looks like this, and we have already discussed about it. Remember, on the first day on the blackboard, if you will again notice the lecture, the first day of the blackboard, basically I have drawn this figure along with the various other features of it. Say, how does the signal looks like after the spectrometer, after the preamplifier, and thereafter when the shaping is done along with amplification, how does the signal look like, the shaped signal. So, and yesterday I've also talked about the scaler and also the single channel analyzer. Now, okay, so this is basically the detector, how it looks like. Now inside this, what you can say, the module that you are seeing right now, we have actually this sodium iodide scintillator detector, which actually looks like this, and this one is put inside this box along with photocathode and the photomultiplier tube, which actually looks like this. So I have taken I am showing you the real world pictures of the detector. Now normally you will not be able to see that because these are encapsulated inside this module over here, and it is quite difficult to put them apart. Okay, and here in this part we have got the preamplifier and other electronic stuff along with the electronics required for giving the high voltage to the sodium iodide and also to the photomultiplier dynode system. Okay, so here yesterday I told you about these three cables which enter the detection system, right? Now these connectors are of BNC type. What I meant to say was these two particular are of BNC connector. They are a typical type of connector we use, and the cable, you see this particular cable, this is used, this you see this knob here, it goes inside like this. It is quite similar to this one here, and this is one we use for basically the high voltage transmission. Now you see in nuclear spectroscopy, for just giving normal bias voltage or taking the input or output signal, the cables are quite different, and also for high voltage the cables are different. We are just showing you here the three different type of cables. Now this one is for this connector is for the preamplifier power. If you remember yesterday I showed you the back of the module, electronics module, and there we have this side sort of connector through which the power to the preamplifier was given. Okay, now again I mentioned this to you yesterday. So this is the lead castle, the lower part of it, and inside this black this wooden box we have the various other sources. They have kept together safely. Now the reason, you see this is quite thick, and the reason was that we want to be safe in the lab while doing other works apart from doing the measurements, radioactive measurements. For that we have to prevent the gamma rays, or primarily the gamma rays which are emitted from the source, put in the box. Now if someone is standing over here, he must not receive the gamma rays. Now for that, what is to be done? We have to put a shield over here. Now what is the concept of the shield? Basically, you remember that the most effective way to absorb the gamma rays is through photoelectric effect. So if we put a very high Z material, since photoelectric effect depends on the Z of a material, right? So if you put a very high Z material along with high density, then the chances of the photon getting photoelectric effect here and being absorbed completely dramatically increases, and as a result the photons will not escape this system and people outside will be safe. So this is the basic idea behind the radiation shielding, and you are seeing one in the diagram right now which is in our lab. Okay, now next, regarding the compact electronics module. So I have shown you the various details including how the knobs work and all that. Now you see this is for our very basic MSc experiment. However, in the real life, when we have to do more complex gamma spectroscopy experiments, then we have to use modules like this. Now this is name based electronics module. It is a standard name, and you can see here it's a sort of various racks, and you can put various modules in this. They are called separate. They are the various modules. Now one of the modules could be the high voltage which we have here. Another module could be the linear spectroscopic amplifier. Another module could be the single channel analyzer, and various other modules which I have not talked to you about. Okay, so this is how things do look like in the real world experiment. So I am showing this to you to, since you are advanced, this is an advanced practical, so you must have a flavor of how things look in the real world where we do nuclear experiment and nuclear research. Okay, now the interesting thing is that you see the back of such bin, this is a electronic NIM based module, right? Now behind the back we have got a jungle of cables like this. So you have to be very careful about which cable you put, and you have to track the various cables in real experiments. Anyway, if you want to get more idea about how these modules look like and how we do experiments, you can check my other videos. Okay, now on to the next slide. Well, you see, I have just tilted this detector setup over here to give you a flavor of what is happening. So you also know this, right? Now, unlike HPG detector, where when the gamma photons directly enter, suppose one gamma ray enters, then after the interaction electron hole pairs are created and they are the real charge carriers. So this is a sort of primary process. However, in this particular detector which we are seeing right now, what happens is that when the incident gamma ray enters the sodium iodide detector, because of the process physics involved, it is converted into a large number of smaller energy photons. Now these smaller energy photons are converted to electrons through this photocathode. So we have got two processes. The first process is conversion of a single gamma ray to a large number of smaller energy gamma rays. Next conversion process, each smaller energy gamma ray is converted to a large number of electrons. And after that, all these electrons are then accelerated through this system, dynode system. And after that, we get a voltage pulse which then enters the preamplifier kept over here. So this is the basic idea behind this entire sodium iodide preamp and photomultiplier tube system. Okay, now again the same thing I have shown here. You see just numbers. So 0.5 MeV gamma ray approximately produces 3 eV gammas, and so you see the numbers how they change, and the FWHM delta E by E I have also shown here to give you a flavor of it. Okay, on to the next part. I thought that maybe some of you would like to revisit this part of the practical, which is a discussion on the components of the gamma spectrum. So I'll be going through it very fast because I've already discussed to you before. Now you see, if we have a source here, and this is the most ideal scenario, that is the best possible case for a gamma ray spectroscopist, full energy peak. The entire energy is absorbed and the electrons are also absorbed in the detector, and we get a single peak, full energy peak. Now we can also have gamma rays as a result. You see, now in case of full energy peak, there was a complete energy deposition. However, in this case, you see, we have incomplete energy deposition. These two gamma rays, they deposit some part of energy and then the scattered photon escapes through Compton scattering. And here I have shown the part. You see, this is the maximum energy deposited corresponds to Compton edge. And we, instead of a peak, we get a distribution. Okay. Now, how do these things look in the real life? To see this, I have shown here the decay scheme for the 60 cobalt. Now you can see predominantly that this decays by two predominant gamma transitions. The 4 plus to 2 plus 1173 and the 2 plus to 0 plus 1332 kV gamma transition, which belong to the 60 nickel nuclei. Okay. Now here you see this 1173 is here. So this is the one of the full energy peak. The 1332 is this full energy peak. Okay. Now, what about the Compton processes? They will be there. The Compton scattering stuff will be there. and it has got two signatures. Number one, the distribution will be there, and number two, this sort of edge will be there. You see this cliff-like structure, falling off cliff-like structure known as Compton edge. Okay, so you see now we have got two gamma energies, right? Now for this 1332, this here, you see this one is this one here, this is the edge for 1332, and this is the edge for 1173. So you see, and the both of the Compton distributions, they are superimposed over here. Okay, now something more is there in this as well. Now it is possible that if we put the source, I'm talking about cobalt 60 source right now. Now if we put the source very close to the detector, then there is a possibility that two different gamma rays, say 1173 and 1332, from two different nuclei, they enter the detector at the same time. And what will happen? The detector doesn't know that they have different origins. The detector will just see the amount of energy deposited, and the amount of energy deposited will be the sum of the two energies, two gamma energies, right? So if 1173 and 1332, two gamma rays enter the detector at the same time, then the detector will see it will respond as if it is seeing a gamma ray which has the summed energy, and you see the effect over here, this. So the detector will show you a full energy peak corresponding to the sum of the two gamma energies. This is known as sum peak. Now in our lab, if we put the source very close to the detector, and if we play with the gain of the amplifier, remember I talked to you about the gain, why I have set to value of 2.0, so that I can observe the 1332 kV below the 10 volt mark. Now if I want to observe the sum peak, then I can change the gain accordingly, and it is indeed possible to see the effect of the sum peak. However, the spectrum that you are seeing right now, you must know that this corresponds to high purity germanium detector. You see the peaks, they are very sharp. Of course, high purity germanium detectors have much high energy resolution compared to our sodium iodide detector. Okay, but even so, the physics will be there, and you will see a sort of broad hump even for the sodium iodide. Now, second thing, the sum peak. So this is the sum peak, right? Now, there will also be a summing effect of the, you see, the Compton edges, the two Compton edges, or this plus this, or this plus this, and as a result, you will see a sort of this structure, this one here. Also, you see, this Compton edge corresponds to that of the sum peak. So overall, a lot of things are here. Now in this spectrum, you can see some other things over there. Let me talk about it now. Well, you see, I have talked to you yesterday, right, that there can be a photoelectric effect on the surrounding wall, and the characteristic X-rays can then enter the detector and be absorbed. And this kink over here, this small peak, corresponds to that of the characteristic X-rays. What about the backscattered peak? You see, the gamma exiting the source, and then from the wall it gets 180 degree scattering, and we can get a backscattered peak. Here you see sort of hump. Why hump? Because we can have the backscattered peak from both 1173 and 1332, and the effect will be quite close to each other in energies. You can do the calculation yourself, and you will find that the two effects are summed over here. Okay, I think I am audible. You guys can hear me, right? Any questions
Yes,
till
sir,
now?
it is okay.
Any question? Okay, so far so good then. Fine. Okay, now you see, we have also talked about the effect of the single escape peak, right? You see here, this small king, it was not present over here. You see, it is not there. Now this small king is due to the single escape peak for 1332. You can do the calculation yourself. 1332 minus 511, it comes around this 800 keV. You see, so this is the single escape peak corresponding to 1332. Also, we can have double escape peak. You see here, again this minus 511, then you can see the double escape peak, and the scenario is like this. We talked about it yesterday as well. Okay, so I have talked to you yesterday, and now I am trying to show this to you for the real case of 60 cobalt. Okay, now also it is possible that the gamma ray 1173 and 1332, they escape our source, they enter the wall, do the pair production over there, and after all that stuff, the escaping 511 kV gamma ray enters our detector and is detected, and then we get a annihilation peak, you see, at 511 kV. So these are all there in reality, and it's a marvelous thing that indeed we can observe this experimentally. So this is a triumph for us, right? So what we are trying to explain through basic physics ideas, you see, after a lot of this electronic jumble and cable and all that, it is indeed possible to see that such things are there. Okay, now on to the next part. Well, a lot of you students asked me yesterday to give you a hint regarding the calculations for backscattered peak and computed edge, and this is what I have shown it for you for the case of 662 kV. You can see on the screen, right? And you must do the calculations for the other gamma rays. For say for example cobalt 60, for that source you should do the calculations and check if you get the backscattered peak in this range, in this energy range or not. You do that by yourself. This should be a sort of easy task for you. So this was a hint I intended to give you. The next hint is I gave you yesterday. This is the data and the corresponding calculations for the standard deviation, right? Root n, this calculation. So this is the data you take from the instrument after you put the 22 sodium source at a certain position from the detector. You get this data, and I gave this data to you as a demonstration. Now see what we can do from this data from 22 sodium. Well, let us first plot this, and as a result you see from this 22 sodium we get this annihilation peak 511 kV and a full energy peak of 1275 kV. Here you see, and this is the Compton edge corresponding to this full energy peak of 1275 kV. So if you do the plot for this, the discriminative baseline in voltage, right, this is in volts as a function of and baseline voltage versus counts, if you do that you will get this. Okay, next what we have done yesterday, remember I told you that from this full energy peak you have to do a sort of subtraction like this, cut it, and then you have to take this peak apart, and for that the calculations I have shown here. You see, from these very values you have to do the calculation. You put the part over here, do the centroid estimate, and then do the calculations I have done over here. And so you can separate out the full energy peak over here. Yes.
স্যার বলছি যে ওই যে বিয়োগটা করছেন, সাবট্রাকশনটা যেটা করছেন ওটা একটু বলবেন ডিটেলে, ওটা বুঝতে পারছি না যে কি বিয়োগ করছেন, কোয়ান্টিটি, যে কোয়ান্টিটিটা বিয়োগ করছেন ওখানে
এই জায়গায়।
হ্যাঁ স্যার, ওইটা তো কাউন্টার, টোটাল কাউন্টার, তার থেকে কি বিয়োগ করছেন?
এই যে এইখানে আমি একটা ব্যাকগ্রাউন্ড আমি কালকে তোমাদেরকে দেখিয়েছি, এখানে আমি একটা লিনিয়ার ইন্টারপোলেটেড লাইন টানবো, লাইন টেনে ওইখান থেকে আমি ব্যাকগ্রাউন্ডটা সাবট্রাক্ট করে নেব। সরি, নট ফর দ্য ফুল এনার্জি পিক, সরি, এইটা ফর দিস পার্টিকুলার কেস অফ 22 সোডিয়াম, এইখানে আমরা ফুল এনার্জি পিকের উপরে কাজ করি না, এইখানে দেখো আমরা অ্যানাইহিলেশন পিকের উপরে করেছি, দেখছো এখানে? সরি, আমি এটা তোমাদের, হ্যাঁ, আমরা এইখানে কেন করি অ্যানাইহিলেশন পিক? বিকজ দিস ইজ ভেরি ইন্টেন্স, ইউ সি this one. So we do this calculation for the annihilation peak, that is 511 keV. You see, আমি এখানে একটা লিনিয়ার ব্যাকগ্রাউন্ড কেটেছি। নাও লুক, this data corresponds to কত? 1 point, say this is 1, this is 1.2, this is 1.4, right? 1.4, দেখো এবার এখানে 1.4 is basically, এখানে আমরা 1.6 থেকে আরম্ভ করেছি, ওকে, this is 1.6, this one. সো এখানে আমি যদি লাইনটা নিই তাহলে লাইনের পয়েন্ট কত হবে? 1.6 এ যা কাউন্ট আছে ও আগের ডেটায় চলে যাও, 1.6 এ কত আছে? হ্যাঁ, রাইট। এর মানে এবার আমরা ওটা বিয়োগ করে নিয়েছি, ঠিক তো? এরপরে 1.8 যেটা আছে ওইটা থেকে আমাকে এই লাইনে যে কাউন্ট আছে সেই কাউন্টটা আমি এইখান থেকে চেক করব, হোয়াট ইজ দ্যাট কাউন্ট, ঠিক আছে?
এবারে ডেটা পয়েন্টের থেকে লাইনটা যেটা টেনেছি সেটার পয়েন্টগুলোকে বিয়োগ করব।
হ্যাঁ, দেখো আমি কালকে তোমাদেরকে ওই ব্ল্যাকবোর্ডে একটা লাইন টেনে টেনে দেখাচ্ছিলাম, ওইখানে ওই ছবিটাতেও ছিল এই জিনিসটা।
হ্যাঁ স্যার, ওটা দেখেছি, তাও একটু ব্যাপারটা পরিষ্কার জিজ্ঞেস করে নিন।
এই যে দেখো আমি তোমাকে দেখাচ্ছি, এই দেখো 1.8 এর কাউন্টটা দেখো কত ছিল, 1.8 এ 24661, রাইট? নাও এবার 24661 এইখানে যেটা আছে তার সাথে এই যে লাইন আছে, লাইনটা এখন এখানে আছে হিয়ার, ওই ভ্যালুটা আমি সাবট্রাক্ট করব। এবার আমি লাইনটা গ্রাফ থেকে নিজেই দেখে নেব যে এটা হয়তো 12,200 এর কাছাকাছি আছে, এটা এস্টিমেশন করতে হবে, এস্টিমেশন, ওকে? গ্রাফ থেকে যা পাবো সেটা আমি সাবট্রাক্ট করে দিয়ে একটা নেট রেজাল্ট পেয়ে যাব, অ্যান্ড ফ্রম হিয়ার উই গেট দ্য সেন্ট্রয়েড করেসপন্ডিং টু দিস অ্যানাইহিলেশন।
বেস থেকে না,
আরেকবার বলো। এই যে দেখো এইখান থেকে এই লাইনে যা পয়েন্ট আছে, হ্যাঁ,
পয়েন্ট থেকে যেটা ইন্টারনাল মানে যেটা ইন্টারসেক্ট করেছে ওই লাইনটার পর্যন্ত যে কাউন্ট হবে সেটা, তাই তো? যেটা সাবট্রাক্ট করছে,
রাইট রাইট। তাই জন্য আমি তোমাদেরকে এই পুরো আমি বেসিক্যালি প্র্যাকটিক্যাল যখন when we do the practical we use both the 137 cesium source and the 22 sodium source. Now this year unfortunately you are not able to attend the lab, so আমি যেটা করেছি তোমাদের জন্য একটা ডেটা সেট দিয়ে দিয়েছি so that you can check how things go, and the next one you do by yourself, the 137 cesium data আমি তোমাদেরকে দেখো এর পরের স্লাইডে দিয়েছি, ওটা পুরোটা করে তোমরা আমাকে,
শোনা যাচ্ছে না ঠিক করে,
আমি বলছি যে here you see 22 sodium data I have given along with the calculations. Now you repeat the same for 137 cesium. দেখো, this is for the 22 sodium and you get the result. After that if you do,
স্যার আপনার নেটওয়ার্কের প্রবলেম হচ্ছে স্যার,
আমি চেক করছি। এনিওয়ে এটা দেখো, আমি পরে তোমাদেরকে লিঙ্কটা পাঠিয়ে দেব। দেখো এবার আমি 22 সোডিয়াম থেকে দুটো জিনিস বার করতে পারি। ওয়ান ইজ দ্য সেন্ট্রয়েড এস্টিমেশন অফ অ্যানাইহিলেশন পিক and another is rough estimation from the just a graph of the full energy peak. These two I can get. Now I have given here the plot for the data for 137 cesium. You do the rest of the calculations yourself. This is what you have to do. This yellow line is basically, this yellow line is the energy calibration. In this part you will have the discriminator voltage, and this part you will have the gamma energy. You know, for 137 cesium full energy peak কোথায় আছে, তার এনার্জি কত, ওইখানে ডিসক্রিমিনেটর ভোল্টেজের করেসপন্ডিং গামা এনার্জি এখানে আছে, আমি পয়েন্টটা পুট করব। ফর আদার কেসেস আমি পয়েন্ট এখানে পুট করব। 22 সোডিয়াম থেকে 511 এর আমি যেখানে পাবো পয়েন্টটা পুট করব, অ্যান্ড ফাইনালি আই উইল ডু এ সর্ট অফ লিনিয়ার প্লট and this is the energy calibration curve. That is, from here, after doing this, if you put any other gamma ray, then you can ask that suppose I have got a 1.2 MeV gamma ray, what will be the corresponding discriminated voltage? Then you can find it out from this plot. Okay.
আমি তো এখানে দুটো সোর্স নিয়েছি, তাহলে দুটো ফ্লো মানে দুটো সোর্সের ক্ষেত্রে আমি এই ক্যালিব্রেশনটা টানতে পারবো?
হ্যাঁ
মানে
দেখো
এখানে তো অনেকগুলো ফুল
137,
এনার্জি পিক আছে।
হ্যাঁ আমাকে বলতে দাও। 137 সিজিএম থেকে আমি কালকে দেখিয়েছি, নাম্বার 1 ফুল এনার্জি পিক থেকে একটা পয়েন্ট পাবো, নাম্বার 2 কমটন এইচ থেকে একটা পয়েন্ট পাবো, নাম্বার 3 ব্যাক স্ক্যাটার পিক থেকে একটা পয়েন্ট পাবো। তিনটে পয়েন্ট পেয়ে গেলাম। ইন কেস অফ 22 সোডিয়াম, নাম্বার 1 511 কেভি, হিয়ার লাস্ট স্লাইড দেখো, এর আগের স্লাইডটা 511 কেভি, এখান থেকে আমি একটা পয়েন্ট পেয়ে যাচ্ছি। সেন্ট্রয়েড কত, সেন্ট্রয়েডে কত এনার্জি আছে। নাম্বার 2 ফুল এনার্জি পিক রাফলি এস্টিমেটেড ফ্রম গ্রাফ, এই পয়েন্ট থেকে আমি পেয়ে যাচ্ছি, এই যে এই ডেটা আর এই ডেটা, এই দুটো থেকে আমি তাহলে দুটো পয়েন্ট পাচ্ছি। আর 137 সিজিএম থেকে আমি তিনটে পয়েন্ট পাচ্ছি। সো ফ্রম দিস 5 plots we can make a sort of linear graph or interpolated graph. Okay,
হ্যাঁ স্যার বুঝেছি।
so this is basically the practical that we have to do.